Hi, and welcome to the first part of calorimetry as part of our thermochemistry unit. All right, so just some basics about a calorimeter. So we know that temperature is the measure of the average kinetic energy of a substance. So basically, how fast something is moving. Delta H, or enthalpy, or the heat of a substance, has to be the transfer of heat energy from the thing that's cold to the thing that's cold from the thing that's hot. It's kind of the backwards way to say it. I guess we should say that the hot thing gets colder and the cold thing gets warmer. And that heat exchange is what we're trying to measure. And the instrument that we use to measure that is called a calorimeter. Now, there are a lot of fancy, expensive calorimeters, but the calorimeter that we use in chemistry is a set of styrofoam cups. So just one, two, and the reason why we use two is because in between here is a layer of air, and that air helps to provide extra insulation, because the whole goal is that any heat exchange that goes on, we want it to stay inside of this cup so that we can capture that exchange of heat as a change in temperature. If all of the heat was allowed to escape to the air, then you wouldn't actually be measuring all of the heat transfer. You'd only be measuring part of the heat transfer, and that wouldn't give you the best data possible. So on the top here, we have also a lid. Styrofoam's good because it's a good insulator, and there's a hole in it for a thermometer. And this isn't the world's best drawing of a thermometer, but this is a thermometer. Now, when we usually do this, we do this with one of those probe thermometers, just the silver probes, and we put that in instead of this. And that gives you obviously better readings. Okay, so the equation that you're going to use for most calorimetry, or really for all calorimetry problems, is going to be Q equals M times C times delta T. And Q is interesting because it really is the same thing as delta T. They're both measuring the heat transfer. It's just a difference in definition. So a lot of times when we solve for Q, we actually want to solve for delta T. And so just keep that in mind, that it's not really a new unit or a new thing that we're trying to learn. It's just some sort of definition difference that we really don't care about. So Q is equal to the mass of a substance in grams. And be careful, because a lot of times with water, they're going to give you milliliters, and you're going to know the grams because the density of water is equal to 1 gram per 1 milliliter. So if you have 50 milliliters of water, you would have 50 grams of water. So just keep that in mind, that this is the density for water. It's not the density for everything, but the density for water. And honestly, you can use it for most aqueous solutions. Okay, so the next one is our C, and that's a constant for each substance. And the one that we really want to know is the specific heat capacity for water, because that's a constant we're going to use all of the time, and that's going to be 4.18. Okay, now what is this constant, the C, the specific heat capacity? It is the amount of energy, so that'd be joules, okay, to raise 1 gram of the substance up 1 degree Celsius. So that's the units with this. So things that are going to have a low heat capacity, specific heat capacity, are going to be metals, because it's very easy to raise them because they're good conductors of heat. The things that are going to have the highest heat capacities are going to be things that are really hard to raise the temperature of it. As I mentioned in class, it's very important to remember, though, that it's per gram. So something like air is going to have a very high specific heat capacity, but we don't really think of air as being hard to warm up, because if you think about it, 1 gram of air would be an enormous volume of air because the molecules are so spread out. So you can't think about it in terms of volume. You have to think about it in terms of grams. So just be careful with that. A lot of things that are going to have high heat capacities are because a lot of the gases are not going to be things we think about traditionally in grams. All right, the final value is going to be delta T. So anytime you have a delta, you know that's a change in, which would mean that it would be the final temperature minus the initial temperature. That's the delta T. So that's the heat exchange that takes place, the amount of energy that something has either gained or lost. And we know that just like with delta H, if it's lost heat energy, it's going to be exothermic and it's going to have a negative Q value. And if it's gained in heat energy, it's going to have a positive delta H value. So let's look at an example problem. So we taken into our calorimeter, our styrofoam cups, and we've mixed 30 mils of 25 degrees Celsius water with 50 mils of boiling water, which we're assuming is at 100 degrees Celsius. Probably by the time you transfer it into the cup, it's not at 100 degrees Celsius, but we'll let go of that. What should be the final temperature of the water? Okay, so in this case, you're going to want to solve for T final. So what temperature did they come to? And we know that it's going to have to be between 100 degrees Celsius and 25 degrees Celsius because this one, the 100 degrees Celsius water, is going to lose heat energy, and the 25 degrees Celsius is going to gain that heat energy. That's the whole purpose of heat transfer. So we're going to come down here, and we're going to write our Q. So the 100-degree water is going to lose heat energy, so that's going to be our negative Q. And what it gains is what the 25-degree water has to gain. So what this one loses, the 25-degree water gains. And for each of these, because Q is always equal to MC delta T, we can plug that in. So for the negative one, we're going to have obviously negative. The mass of this is 50 mils. So we're going to put in 50 grams because remember when the screen before we said that density of water is 1 gram per 1 milliliter. The specific heat capacity of water is 4.18. And then we're going to have T final, which is what we're trying to solve for. That's our X minus T initial. Well, the initial value of that is 100 degrees Celsius. Okay, so now our positive Q, the one that is gaining in heat energy, is our 25 degrees Celsius water, and we have 30 mils of that. So we'll plug in 30, 4.18, and I'm going to have to squeeze this in here, T final minus 25. And the temperature values you can put in Celsius or Kelvin. Because it's a delta T, the difference between them is going to be the same. All right, so now this is basically a giant algebra problem that you need to solve. And so the delta T, let's see, our T final is going to be 2. Okay, so now I just multiplied through. I took these two numbers and multiplied them, and then I distributed to here and here. Be very, very, very careful with this sign, right? Let me highlight this for you. That sign right there, because this is a negative times a negative, so it becomes positive. So just be really careful with that being a positive sign. And then if we look over here, you've got these two numbers, and you're going to distribute it here, and that value is going to be a negative value, okay? All right, so now I'm going to take the two factors, and I should actually have a TF with that one. So now I'm going to take my two factors that have TF, which is going to be right here, and right here, and I'm going to add those together, and I'm going to get 334.4 T final, and I'm going to take, I'll change the color so you can see, kind of writing all over the place here, this value, and I'm going to add those together because this has got a negative sign, so when you add it, you guys know algebra, you're going to get 24035, and now it's just a matter of dividing both sides by this value, and you're going to get, let me put it in my calculator here, 34.4 is equal to, D final is equal to 71.9 degrees C. And this value makes sense. You should always go back and think about it because it has to be in between 100 and 25. And it should be closer to 100 because you have more of the 100-degree water than you have of the 30 ml water. All right, let's take a look at another problem. Okay, so this one we're probably going to have to write on the next page. We have 100 degrees of 20 Celsius water, and it's added to a calorimeter. 4 grams of silver is heated to 400 degrees and is added to the water. The final temperature of the water is 30 degrees C. What is the specific heat of the silver? Okay, and I realized here, sorry, I had to stop it for a second. The pen didn't pick this up correctly. So it actually should have been 40 grams of silver, and it should have been heated to 900 degrees Celsius. If you do it the other way, you can still solve for it. The specific heat of your silver rather, is just going to come out to not be the value if you were to like look it up on Wikipedia. Because you can look up the specific heat capacities of substances on Wikipedia or online. They have data tables of them. Though they'll frequently be in calories, because in the American system we use calories instead of kilojoules or joules. So the values will be different anyways than we should calculate. But needless to say, we're going to calculate this with the values that we know work and that give us the right answer. Okay, so when we set this up, again, we're going to say that Q for the silver. So silver is the one that's hot and it's getting colder, so it's giving up heat energy. That's going to be our negative Q. Has to be equal to the Q for the water, which is gaining in heat energy. So if we look down here, we're going to do negative Q. So that's going to be 40 grams, because that's the amount of silver. So our mass is going to be 40 grams. Specific heat of silver is what we're solving for. And the change in temperature. Well, we're going from 900 degrees C to 30 degrees C. So it's changed by 870 degrees T final. This would be my T final. And this would be my T initial. And we also have to remember out here that since this value was negative, we want to make sure we leave our negative sign. That's a negative. Okay. All right. And so our positive Q is going to be the water. So we have 100 mils of water. We know that's 100 grams of water because the density of water is 1. And the specific heat of water, we do know that's 4.18. The specific heat capacities on both sides do not have to be the same. In the last case, they were the same because they were both water. And the change in temperature of this is going to be from 20 degrees C to 30 degrees C, which is only a 10 degree temperature difference, and it's in the positive direction. All right, so basically we're just going to do some algebra and we're going to solve for C. And one of the things you have to be careful of is because this is negative and over here, these are both negative, these actually cancel each other out and they become positive. So basically all you have to do is multiply these three values together, multiply this and this together, and then divide to solve for C. And you end up getting that C, our specific heat capacity for silver, so I'll put subscript AG really small there, I don't know if you can see it, is equal to 0.12, and the units for this are going to be joules